Okay, so welcome to the next lecture of Parameterized Algorithms. I am now sharing the whiteboard with you. You should see now the lecture notes on which I will be showing you around, and the topic of today's lecture, and actually of the lecture that will be also next week, is the treewidth of a graph. So today it will be treewidth 1. Next week it will be treewidth 2. So today we will talk mostly about like standard tree decompositions of graphs and how to deal with them combinatorially and how to do dynamic programming on tree decomposition. Next week we will be talking more about applications in various parameterized algorithms of interest. Good. So the main idea of treewidth is to measure how much a graph resembles a tree. So on the left side here, you see a tree. Well, it's just a graph that is acyclic. And on the right-hand side, you see a graph that sort of is not necessarily a tree, so there are multiple cycles in this graph. But when you look at the structure of this graph, you sort of see that it is sort of tree-like, right? So treewidth is a structural parameter of a graph that sort of measures how tree-like a graph is. So in order to measure this is actually non-trivial combinatorial definitional task, how to measure being close to a tree. There are multiple ways of measuring this. Treewidth is just one option, and there are also a few different definitions of treewidth. We'll see, I think, at least 3 of them today. And the most intuitive, at least for me, is the one that goes through so-called tree embeddings. So imagine that you've got a graph G, and we would like to understand that the structure of this graph is sort of tree-like. Yeah. So an embedding, a tree embedding of G into a tree T, yes, it's an embedding that looks as follows. Yeah. So an embedding will take a vertex of a graph, say U, and it will map every vertex of a graph to a connected subtree of a tree. So I fixed some tree T that is my shape of into which I will try to squeeze my graph. And I would like to now take every vertex U and map it to a subtree U of T. Yeah, so I want to take this vertex and kind of smear it onto a connected subtree in T. And the rule is that whenever I have an interaction between two vertices in the graph, in the sense that they're connected by an edge, I should have an interaction between their images in the tree, in the sense that when I look at the image of one of them and the image of the second of them, they should non-trivially intersect, right? So let's see this on an example, because this might be a dry definition so far. So on the left-hand side, you've got the graph G, yes? And on the right-hand side, you've got a tree T. This is actually a claw, a star with 3 leaves, so a very simple tree. And I would like to squeeze this graph G into the shape of this tree. So how I do this? So I take, for instance, this vertex, this purple one, and maybe I will map it to a single vertex tree that is just somewhere here. Yeah, that just consists of this one node of the tree. But for instance, the red vertex, I will smear onto a larger connected subtree consisting of these 3 nodes. Yeah, this node, and this node. So if this is vertex U, then this red subtree here is eta of U. Now the blue vertex here, I can smear, for instance, well, I should be together in some node with the purple one, because there is an edge between the blue and the purple. So I should be here. But also I need to be, for instance, in the future, I will need to be together in some of the nodes with this orange one down there. So maybe I will embed it like that. Yeah. So the blue subtree corresponding to the blue vertex consists of these three nodes: the central one, and this one. Yeah. Then the light green one, this one here on the top right. Maybe I will again do similar as the purple one. I will just embed it into a single node tree here. The dark green one, the one here, similarly, I need to be in this node, yes, and because I need to be together in some node with the light green one, and maybe I'll draw it like that, just to leave here the room for the orange vertex, which is the one that I will map to the node in the bottom. Yeah. So now when you look at this graph, you see that whenever I have an edge in the graph, for instance, between the red and the green, yes, I see that there is one node of the decomposition, for instance, the middle one, yes, that contains both the red and the green, yes, and that's the rule that whenever I've got an edge here, this edge should be contained in one of the bags. And in this way, the structure of the graph in the left is sort of preserved in this embedding. Yeah, we see this interaction in this model in the tree. Okay, so this is the definition of a tree embedding. So maybe quick poll of +1s if this is clear, or are there any questions at this point? So if this is clear, please put a +1 in the chat. Okay, I see a wave of +1s. Okay, so this is so far a way of understanding how do I squeeze a graph into into a shape of a tree. So now, with each node of this tree T, for instance, this node X that is in the middle, I can associate a bag, and the bag is the set of all the vertices that are contained in this node. Sorry, of all the vertices for which this node participates in their subtree. Yeah, so for instance, for this bag, maybe not this color, for this bag, for the central node, the corresponding bag consists of the red vertex, the blue vertex, and the dark green one, right? And for instance, this node corresponds to the bag consisting of the purple vertex, of the red vertex, and the blue one. Yeah. So observe that these bags are not necessarily disjoint. Yeah. The blue and the red actually are both in both of those bags. Yeah? So a bag of a node is just the set of all the vertices of my graph G that are that contain this node in their corresponding subtrees. Yeah, so let's see what this bag function satisfies. First of all, if I look at any particular my favorite vertex of a graph, then when I look at all the nodes that contain this vertex in their bag, then this must be a connected subtree of T. Yeah, because this is just this thing is the same as simply eta of U in our tree model setting. Yeah, so this is just the subtree consisting of all those bags that that contain my vertex U. And the second condition, the fact that whenever I have an edge in my graph, the corresponding to subtrees intersect, it can be rephrased in terms of bags as follows: that whenever I've got an edge in my graph, there must exist a vertex in my tree whose bag contains both of the endpoints. Yeah, so every edge must be entirely contained in one bag. And if you've got a tree T and a mapping beta that maps maps the nodes of the tree to subsets of vertices called the bags, then this is a tree decomposition if this tree and the mapping satisfies those two conditions. So now, a trivial observation, maybe not so trivial, but an easy observation is that actually these 2 points of view are equivalent. The point of view via tree embedding and the point of view of via tree decomposition, I can go from one to another. Yeah, so for instance, if I've got a tree embedding given, I can make a tree decomposition by just saying, yeah, for every node of my tree T, I just record which of the vertices have this node in their subtree, and this is my back function, and it satisfies those 2 conditions P1 and P2. On the other hand, if I've got a tree decomposition, yes, I can go back. Yeah, so I just argued that from a tree embedding I can make a tree decomposition, and if I've got a tree decomposition, I can make a tree embedding by just looking at this definition. Yeah, so in order to define eta of a vertex, or how a vertex is mapped to a connected subtree, I just look at the subtree consisting of all the nodes whose backs contain the vertex. And by condition P1, if condition P1 is obeyed, then this subtree must be connected. And then condition P2 corresponds to this condition that whenever I have an edge, the corresponding to subtrees of the endpoints intersect. So this is the notion of a tree decomposition. And this is the usual language that we are speaking about when talking about Treewidth and tree decomposition. So whenever you look at the literature and you see any paper on Treewidth, usually the tree decomposition will be defined in this way via the back function and the conditions P1, P2. However, I define this also via tree embedding because I think that graphically it is easier to grasp it in this way. And in both cases, this is a way of expressing the structure of a graph in the shape of a tree. And that's the main point. So now if we are trying to express the graph in the shape of a tree, we would like to understand what does it mean that such an embedding or such a tree decomposition is good, in the sense that it really shows that a graph looks like a tree. And for this, we will use the notion of the width of a tree decomposition. So the width of a tree decomposition is simply the maximum back size minus 1. This minus 1 maybe will become clear in a moment why we subtract 1 from the in this definition. So essentially, I will say that a tree decomposition nicely models how a graph looks like a tree if at every node of my tree decomposition only few vertices interact with each other. Yes, there's only a limited number of interaction between the vertices, and this interaction is bounded by the width of the decomposition, which is just the maximum back size minus 1. And the tree width of a graph is the minimum possible width of a tree decomposition of G. So in this minimum, we can choose the shape T, the shape of T. So we can take any shape of a tree we like, into which we embed, and any kind of embedding we would like to we wish to imagine, and then we measure the maximum back size of this. Yeah, so how well we can think of a shape of a tree and squeeze the graph into this shape of a tree. Good. Are there any questions at this point? We will see some examples in a moment, but maybe there are some questions to this definition. Can I get some +1s in order to feel secure that you are on the same page? Good. I'm happy to see some +1s. So let me continue with some examples. So let's see. Definitely, we would like to have the situation where whenever I'm looking at a tree should be definitely tree-like, right? So let me think how a tree I can express. I can find a tree decomposition for a tree or a tree embedding. Okay, so maybe. Yeah, here is a tree. here I just copied this tree because I will be using the same tree as in order to embed this, the original tree in. So I have now the graph G, which is here, yes, and I would like to find a tree decomposition of this graph. It will be called T. Maybe I will make it of a different color, maybe blue. Yeah. So now for every vertex of my tree, for instance, the red one, yes, I would like to, I will think of tree embeddings for starters. So I would like to embed this vertex into a connected subtree of this tree. So how I will do it, I will embed every vertex to a subtree consisting of this vertex and its two sons, two children. So for instance, this vertex, the green one, will be embedded to a subtree consisting of like that. Yeah. Then, for instance, the orange one here, yeah, and say the blue one, for instance, here will look like that. Okay, I hope that you see the pattern here. So now observe that whenever we have an edge of my original graph, this edge is entirely contained in one of the backs. Yeah, because the backs, for instance, the back of this vertex here, it consists of these two vertices, the orange one and the red one, and then every edge of my graph, yes, is contained in the back of the lower end. So I use the same tree to make a tree decomposition, and the tree decomposition consists of for every vertex, yes, I associated with it a back consisting of this vertex and its parent, which corresponds to the tree embedding being an embedding where every vertex is being smeared onto itself and all its children. Yeah? So now you see that every bag is of size at most 2, which means that the width of this decomposition is the maximum bag size minus 1, which is equal to 1, right? So we have just proved that trees indeed have tree width 1, because we can always find a tree decomposition of width 1. Good. And actually, during the tutorials, maybe there will be an exercise showing that forests are actually exactly graphs of tree width 1. So let's look at a more difficult example, namely when the graph in question is a cycle. Yeah. So I drew the cycle already in a sort of prepared way for making tree decomposition. And maybe now I will start with looking at the tree decomposition. Let me draw the consecutive bags. So this will be my first bag. Then this will be my second bag. Yeah. Then this will be my third bag. Yeah. This will be my fourth bag. So you see that the bags sort of sweep the graph from left to right. So in terms of the tree decomposition, this corresponds to a tree decomposition being a path, yes, where every vertex is being smeared onto two consecutive, one or two consecutive nodes. Yeah. Apart from this topmost vertex, say the blue one, yes, which is being smeared onto everything. Yes. So in this way, we have an interaction between every two consecutive vertices on this path along this decomposition. But this one vertex on the top is being put everywhere in order to have interaction between the beginning of the path and the end of the path. Yes. And now you see that here the bags, yes, corresponding to those sections of this decomposition or to bags drawn here, they are of size 3, which means that the width of this is 3 minus 1 equal to 2. Yeah. So observe that in this example, the decomposition is a path, right? Which is a special kind of a tree. So we define path decompositions as decompositions that are paths, and the path width of a graph is the minimum width of a path decomposition. So in this way, we have proved that cycles have path width at most 2. Yeah. Sorry, minimum of a path decomposition, and the width is defined the same way in the sense that maximum backsize minus 1. Okay, so let's see one more example that will turn out to be important in during the next lecture, namely a grid. I will not draw a full decomposition here. I will just draw consecutive backs to you. So here is a k times k grid. K on one side, k on the other side. So now how I would like to make a tree decomposition of this graph. This graph doesn't look tree-like, right? A grid is sort of bidimensional. It is rather square than tree-like. But still, I claim that the tree width of a grid is at most k. Why so? So I can make a path decomposition, even path width is at most k, by making, for instance, the first back, let's say that it is the first column. It has size k minus 1, so I even have a 1 less. And then let me sweep the grid by going from one column to another column. So how do I do this? I make then a back looking like that. Yeah, so I just moved one leg here. And then what I can do, I can then jump from here to here, sort of like abandon this vertex because I already sort of processed it. And now make a back consisting of those vertices. Next, I can jump further and make a back consisting of, those vertices. Yeah, and so on until I finally sweep this whole first two columns. I get a back like that, and then I can continue with the next column. Yeah, then I start to process the next column from the bottom, and so on and so on. Yeah, so this is a sequence of backs, and you can easily check that it satisfies all those properties. Whenever I look at a particular vertex, it appears in a sequence of in a contiguous intervals of backs. So here the backs are of size k plus 1, yes, which means that the width is equal to k. And this is actually optimum. We will argue this sort of next week, but the tree width of a k times k grid is therefore equal to k, and the way to see it is that you sweep the grid from left to right. Okay, are those examples clear? Are there any questions at this point? Okay, no questions so far. So there's one more important observation about tree width and how to view tree decompositions, namely the view through separations. So imagine I've got a tree decomposition of a graph G, say that it has a width at most k. Yes, and let me look at one edge of the decomposition. So this edge connects to nodes of the decomposition. So these two nodes are associated with backs, say a back like that and a back like that, and these backs can intersect as any two backs in the decomposition. So let me look at this intersection. This intersection is called the adhesion of an edge of the decomposition. So the adhesion of an edge of the decomposition is just the intersection of the two backs. Yeah. So now when you think about this edge, yeah, then maybe let me remove this. Then this edge splits the whole tree into two subtrees, as every edge in a tree, into the left subtree and the right subtree, the green one and the red one. Yeah. So now when you think about vertices of my graph, all the vertices of my graph are either live on the left side or live on the right side, or they go across this edge. Yeah. So for instance, a vertex that whose tree embedding looks like that, it entirely lives on the left side. Yeah, a vertex whose tree embedding looks like that entirely lives on the other side. However, there can be also vertices that live both on the left and on the right, and they need to be in this adhesion, right? Because in order to cross this edge, yes, I need to be both in the back of X and in the back of Y. Yeah? So I can classify all the vertices into those three types. Yes, guys that are on the left, guys that are on the right, and guys that are in the adhesion. And observation is that these two are non-adjacent. Because if I have a vertex whose tree embedding looks like that, is entirely on the left, then definitely it cannot share any back with a guy that looks like that is entirely on the right. Yeah, because they are never together in a back. So I will not have any edges looking like that here. So this means that every edge of the decomposition corresponds to sort of a separation between in the graph, and the separation is a triple AXB such that there is no edge between A and B, and this should be a partition of the vertices of the graph. Yeah, so this is the definition of a separation. And observe that the size of this adhesion, set, the intersection of the backs, is definitely bounded by the sizes of the backs, and actually by the sizes -1 if I assume that the backs are pairwise different. I can always assume this because whenever I have two neighboring backs with exactly the same, two neighboring nodes with exactly the same backs, I can always contract this edge and just keep it once. So this means that the adhesions are, I can assume that they are of size at most k, and the edges of my tree decomposition, they correspond to separations of order k in my graph. Yeah, to ways of cutting the graph into pieces A and B using a small separator X. Yeah, and this is how you can also view tree decompositions. Tree decompositions are sort of like tree-like organizations of separators in the graph, and these separators are non-crossing because whenever I'm like shielded by some other separation sometimes like an edge that is deeper in this tree, it will carve out only a subset of what the higher edge is carving out. So you can also view Treewidth like that. Okay, so this was essentially the definition of Treewidth and how to view Treewidth in a combinatorial way. So are there any questions to this combinatorial part? And otherwise, please put a +1 if you're happy with this explanation.
Does this in any sense give us all the separations of some order, or?
No, it not necessary. Not necessary, because they can be crossing ones, right? And whenever I have two crossing separations, if I'm thinking about making a tree decompositions, I need to pick one of them to the tree decomposition. But there is something to your question. I will not go into the details here. There is a notion called tangles in graphs, and which are sort of highlighting every separation in the graph, and there are closely related to tree decompositions. Good. So if there are no further questions, let me look at the next topic, which is a topic that maybe sound boring at the beginning, and it's not the most fascinating topic in parameterized complexity in general, but it is immensely important for all the possible applications of Treewidth, namely dynamic programming on tree decomposition. So the idea is that we have seen that this Treewidth can be thought of a way of sweeping the graph. And when you know something about dynamic programming, you've seen some dynamic programming algorithm. They usually, you can think in this way, that you have some large object and you can sweep it in some sense, always keeping a limited amount of information. In particular, when you have a tree, there are many dynamic programming algorithm on trees that proceed in a bottom-up way, always keeping some information about the subtree. Yeah. So, for instance, if I'm thinking about some combinatorial problem in a tree, maybe I can do bottom-up dynamic programming, remembering what happens in the subtree subject to some condition what happens in the root of this subtree. And this will be exactly the situation in dynamic programming on tree decompositions. Namely, we'll try to sweep the graph from bottom up in a way that constructs partial solutions for subtrees of this graph, for subgraphs of this graph. And the subgraphs that we will be thinking about correspond to subtrees of the graph. And so, for instance, if I have here a subtree of the decomposition, this corresponds to a subgraph consisting of all the vertices that are sort of happen here. And these vertices that happen here, they can communicate with the rest of the graph only through this back, the back at the root. Yeah. And this is the separation property that we have. So all the vertices that are here and are not contained at the back, they will not have edges to the rest of the graph, which sort of separates our problem into pieces. And we will try to sweep the tree decomposition bottom up while thinking about, while keeping partial solutions to the problems we are interested in. So there are many different ways of expressing, of presenting such dynamic programming algorithm. In the Platypus book, you see the classical way via so-called nice tree decompositions. I will give you here a alternative view, which over the years I converge to the conclusion that this is actually a better way of thinking about this. We will think about boundaried graphs and operations on boundary graphs. It's essentially the same language. It's just presented a little bit differently. So what is a boundaried graph? This is a very easy definition. A boundaried graph is just some graph G, and I've got a subset of vertices called the boundary of G. Yeah, here, which should be small, and which is considered sort of an interface to the outside world. So maybe there is some outside world here, and this graph will be glued along this interface to the rest of the world. So the definition is just a graph together with some subset of vertices, and this subset of vertices should have a small size, should have size at most p. When we're talking about a p-boundaried graph. So then when we have this p-boundaried graph, we can make some operations on them. Yeah, for instance, we can introduce a new vertex. So by introducing a new vertex, I mean adding a new vertex to the graph. Yes, for instance, this blue one that is here. And I can also add some edges to it, add an incident to it. And these edges, the rule is that I can add edges only to other boundary vertices. So I can, for instance, add those 3 edges, but I cannot add any edge to any vertex that's already forgotten, in the sense that it's already not in the boundary. So this is the introduce operation on a boundary graph. Another simple operation is the forget operation. So I just remove some vertex from the boundary. Yeah? So for instance, here you've got this pink vertex. Maybe I do not need it anymore, so I'll just forget it from the boundary. Yeah, the ground graph stays the same. It's just that the boundary with the changes. And then finally, the interesting operation is the join operation. Yeah, so we have 2 boundaried graphs, say G1 and G2, and I can make their join, G1 join G2, as follows. I just put them next to each other. I pick an arbitrary bijection between the boundaries. The boundaries should be of equal cardinality. Oh, sorry, this is not how the colors should work here. So I pick an arbitrary bijection between the boundaries, and I just fuse the vertices that are to be fused. Yeah, so that are corresponding to each other in the bijection. Yeah, so I just put the take the disjoint union and I merge the boundary vertices. So for this to be applicable, I need that the boundaries are of the same same cardinality. Yeah. So this is a binary operation in the sense that it takes two boundaried graphs and outputs one boundary graph. Yeah. These are unary operations in the sense that I just do something with one boundaried graph and output another boundaried graph. And I will also have a trivial nullary operation. So it's just a constant. It's an empty boundaried graph. So a graph that doesn't have any vertices or edges, and this is empty boundary. Yeah. So these are four operations that I can work with on boundaried graphs. And note that one of them, the introduce operation, I can think of it, I can even break it into smaller steps. I can always first introduce the vertex being isolated. So for instance, if I have some boundary vertices that I have here put in blue, maybe I just add one new red vertex, red boundary vertex that is so far not adjacent to anybody. And then I can make a sequence of introduce edge operations that introduce the consecutive edges that are incident to this vertex. Yeah, so I can always break an introduce operation into several into operations of introducing an isolated vertex and then introducing edges one by one. And the introduce edge operation just introduces a new edge between two boundary vertices. Yeah, it's important that only boundary vertices can be affected by this operation. Right. So the fact that is important here is that these operations on boundaried graphs, they exactly characterize Treewidth. So we will prove in a moment, and this proof is not hard at all, that the graph has Treewidth at most k if and only if I can construct it using those operations from empty graphs. Yes. So if and only if G can be constructed in this algebra of k+1 boundaried graphs. They should the boundaries should be of size at most k+1 at every point because the backs should be of size at most k+1.
Excuse me, can you repeat how we do join operation?
Yeah.
Because
how we do join operation.
Not get those colors in the intersection.
In order to make a join operation, a join of two boundaried graphs, G1 and G2, yeah, we need to take those two guys, and we need to put them next to each other, so take their disjoint union. And we need to specify how are we joining the boundaries. So we need to specify a bijection between the boundaries. And then what I'm doing, I'm just taking this vertex and identifying them into one. Taking this vertex and identifying them into one. Maybe an example. So say that I'm joining a triangle with this being boundary vertex 1 and this being boundary vertex 2 with a, say, a 4 cycle with this being boundary vertex 1 and boundary vertex 2. The numbers give me the bijection. Yes. So the result of this join will be a graph that will look like this. Maybe a green one. Like that, because I glued 1 and 2 together, ones into one vertex and twos into two, and the edge, and the new boundary is the consists of both those of those fused boundaries.
Okay.
Yeah. So this is an operation of gluing graphs in a sense. You should think of this like that, along small interfaces. Good. So now let's prove this theorem. Let's prove this fact that I've got Treewidth at most k if and only if I can construct my graph in this algebra. So actually both of the implications are very easy. So if I've got the tree decomposition of width at most k, and I would like to construct the graph in my algebra using consecutive operations. So what I do, I will process I will root the decomposition. So I can assume that my decomposition is rooted. by just routing it in an arbitrary bag, say this one green here. Yes, and then I will proceed bottom up in this rooted tree by constructing subgraphs that correspond to larger and larger subtrees. So whenever I'm, for instance, processing this subtree, I have processed this subtree, I should create a subgraph. I should construct a subgraph consisting of all the vertices that participates in those bags. So all the vertices that are somewhere here. Yes, with the root bag being the boundary. Yeah, so if this is my vertex X, my node X, then I will construct a graph GX consisting of all, this is the subgraph induced by all the vertices here, and the boundary of GX should be the root bag. Yeah. So now what I want to, so imagine that we have already constructed this subgraph with this being the boundary, and this subgraph with this being the boundary. And now we would like to construct the whole thing with this being the boundary. Yeah. So first of all, let me look at this bag, the green one, and this blue one. Yeah. So in the graph, they actually intersect. They may intersect. Yeah. It can look like that. Yeah. And here is the adhesion of this edge. So now if I want to move from this boundary to sort of this boundary, what I need to iteratively do, I need to first forget all those vertices. Yes, because they will not be boundary vertices anymore. And then I need to introduce all those new vertices. Yeah, so instead, when going from this graph to a graph that looks like that, yes, with this being the boundary, I can do it by iteratively first forgetting the vertices from the difference and then introducing new vertices from the difference. And in the same way, I can move from this blue graph with this being the boundary to this graph with the topmost bag being the boundary, and so on and so on. So once I did this, I can just join all of them because now the boundaries are the same. Yes, with the obvious bijection doing this. So I just join all the subtrees by doing it one by one. Yeah, because the join operation is binary. I can join them in any order. Good. So this was one implication. It's just a bottom-up process that constructs the graph according to the tree decomposition. The other implication is actually even simpler. Namely, if I think about what is actually a construction in this algebra of boundaried graphs, it's actually a term, right? Because I have those operations. The leaves are actually empty graphs always. So this is the only nullary operation that I have. And I have operations like introduce, which are unary. They have only one child always. And I have joins, which are binary, and they correspond. They have always two children. So this already gives me a tree, and this will be exactly my tree decomposition. So the tree of my decomposition, if I now go through from this construction term to a tree decomposition, the tree of the tree decomposition will be exactly the tree of this term. And how I define the bags, I just associate with each. So every node, for instance, I don't know, this node, yes, it corresponds to the subgraph, the boundaried graph that is being constructed in this subterm. And this subgraph has some boundary vertices. And with this one, I associate the bag being the boundary vertices at this point. Yeah. And then you can easily see that that if you define a tree decomposition, if you define the back function in this way, then it is easy to check that that it satisfies all the requirements. When you look at a particular vertex of the graph, it lives in a connected subtree of the backs. Good. So maybe it may be a little bit confusing at first glance what happened here, but this is essentially a syntactic manipulation of between the definition of a tree decomposition and the definition of a construction term in the algebra of boundaried graphs. The only non-trivial part is the fact that when moving from one back to another back, I need to iteratively first forget vertices and then iteratively introduce new ones. Good. Are there any questions at this point for this proof? Can you put +1s if you are on the same page? Good. So let's continue further, because now that we define this this algebra of boundaried graphs, this is the suitable language to write dynamic programming algorithms. So essentially, when you think of this constructing the graph as a bottom-up process that adds new vertices and merges parts of the graph, and at every point I have already constructed some part of the graph, which is a subgraph H here. Yes, together with the boundary of H, and the future, whatever will happen later in the construction, will be interacting with the subgraph constructed so far only through this boundary. Yeah? So the idea is that when doing dynamic programming in a bottom-up way, we will record the optimum solutions for the subgraph H. But the only thing that we need to care about sort of is the behavior of a partial solution on this boundary, because the boundary is the only place that will interact with the future. So whatever happens in the past, yes, we can abstract away to what happens in the boundary. This may seem a little bit confusing at the first glance, so let's see some on some examples. So the most trivial example is the maximum independence set problem that hopefully you have seen already at some point. So in this problem, we are given a graph and we want to find the maximum set of pairwise non-adjacent vertices. So for instance, in this graph, I could pick this one, and this one, and I would like to maximize the number of vertices picked subject to the fact that they are pairwise non-adjacent, like in this solution. So if I am given some induced subgraph H with some boundary, what would be a partial solution in the subgraph? Well, it would be a way of selecting an independent set within the subgraph. Yes, maybe also selecting some vertices from the boundary. So this will be a partial solution that we will be interested in. Yeah, so just an independent set in my subgraph. So now imagine that we are now doing this dynamic programming and there will be some future happening. Yes, later I will add some more stuff to the graph. So observe that this stuff that I will add further on will never be adjacent to those vertices that are not in the boundary. So these vertices actually do not count, they do not contribute to any constraints that I have in the future, in the sense that it only matters for possible extensions of this independence in the future what I picked from the boundary, because these are the only vertices that can block something from the future to be picked. Yeah? So the behavior of a solution on my boundary of H will be just the intersection of my partial solution with the boundary vertices. Yeah? So now I can define the function in the dynamic programming that we will be doing. So whenever I've got my subgraph H, I define this function phi H. This is the dynamic programming function. Make programming. Yeah. So this is a function that is defined for a boundaried graph H. Yes. And as an argument, it takes a subset of the boundary, which is the expected intersection of a solution with the boundary. And the value of the function is just the maximum extension size. It will become clear later on why I define it this way. Namely, whenever I have decided that from my boundary, I will pick some set X, I would like to record the cardinality of the best possible extension from this boundary to the rest of H. Yeah, so the value of phi on x is the maximum size of an S in the rest of the vertices, such that together with x, they form an independent set. Good. So now the idea is that we will compute the values of this function in a bottom-up manner over the tree decomposition. So is the definition of phi clear? Because that's the most important part always when writing a dynamic programming algorithm, deciding exactly what we will compute. Are there any questions? Maybe a plus ones wave would be handy. Okay, I see some. Are there any doubts at this point? This is just a definition of a mathematical function that for a boundaried graph, it outputs some values. Okay. So as we define this function, and we would like to compute the values of this function on the tree over this construction term, we'll do it bottom up, and for this we need to give some recursive equations on this function. There are some recursive formulas. So let's start easy. What happens when I have an empty graph? Well, then there is only one subset of the empty boundary of this graph, which is the empty set. Yeah. And then the best possible extension, there's only one possible extension being the empty set, and it has cardinality 0. Yeah. So the beginning of sort of a recursion is the base of the recursion is clear because we only have value 0. So then what happens when I introduced a new vertex? Let's say that I will use this, introduce isolated vertices, and then I will introduce edges. I will introduce edges one by one. Yeah, so now my new boundaried graph H is obtained from a previous boundaried graph H prime by introducing a new vertex U. Yeah, like on this picture. Yeah, so now U is a new boundary vertex, and so far it is isolated. Yeah. So observe that now I would like to understand what is how I should compute phi of a subset X, which is a subset of the new boundary. So this subset either contains U or not, but independent of that, yes, whether it contains it or not, this vertex is isolated. It doesn't pose any problems with respect to the vertices here. So whenever I decided to pick from the previous boundary some vertices here, yes, then meaning I can just read what is the best possible extension from the pre-computed dynamic programming table. Yeah, so phi of x, the new phi of x is just the old phi of x, possibly excluding this vertex u, which is taken or not. Yeah, it doesn't affect the size of the possible of the best possible extension. So now what happens if I introduce a new edge, say an edge UV between two vertices? So now observe that if both of these vertices are in my set X, so I told myself that I should take both of them to the independent set, then actually it doesn't make sense, right? Because then I would be forced to pick two vertices that are adjacent to the independent set. So I should put a minus infinity, indicating that there is no extension at all in this case, because whatever I will pick from the rest of the graph, I will never make an independent set, because already these two guys are not independent. However, if they are not both contained in the in S, for instance, only one of them is contained, then this edge doesn't affect any constraints for an independent set. Yeah, so the possible extensions to the rest of the graph are exactly the same as if this edge was not present. Yeah, so I can just get the pre-computed value from the previous boundary graph before adding the edge. Okay, so next we can forget the vertex. So here we've got the old boundary, which included some vertex v, yes? And now we are forgetting it. Yes, so now the new boundary graph H will not have v as a boundary vertex. However, it was included in the boundary of H prime. Yeah? So now if I would like to understand what is the best possible extension of, say, a set that looks like that. Yeah, this is a subset X of the new boundary. Yeah. Then, well, the extension of this independent set into graph H, it might have included V or not, right? So either it did not include, and it therefore is contributing to this factor, yes, to just saying what was the best possible extension in the previous graph when from the boundary I only take X, or it was included. Yes, and now we forget it, so it becomes from a vertex that was in the boundary, it becomes a vertex from the extension. So this is why I add a +1 to this value. Yeah. And finally, if I'm joining two graphs, H1 and H2, and I would like to understand, for instance, for this subset of the boundary X, what is the best possible extension to the graph to the rest of the graph consisting of both H1 and H2, then because between H1 and H2 there are no edges at all, yeah, because we were doing the join operation. The join operation doesn't introduce any edges between the forgotten vertices. I essentially now only independently can extend the solution to here and extend the solution to here. So in order to get the best possible extension for a set X in the graph after the join, I take the best possible extensions in the graph before in those two partial elements of the join operation. Good. So this was an explanation of the dynamic programming formula. So I have given dynamic programming formulas for all the 5 operations on boundaried graphs. So any questions to those formulas? Could you put +1s if you are happy with this explanation? Good. I see some +1s, so hopefully, yeah, Jack, quite so. Do you have any specific things that I should explain further? No, I don't. Okay, so yeah, dynamic programming has it that sometimes you need to stare a little bit and understand what's actually happening. The good thing about this formulation is that there's a precise mathematical function that we are trying to compute, which is a function from boundaried graphs to integers, and we are just saying we are just giving formulas for this, so you can look at this formula and you can analyze it and understand why the formula is like that. Okay, so now given those formulas, we can write an algorithm that computes all those values. So if I'm given a tree decomposition of a graph, and we'll usually assume that the tree decomposition has always as many nodes as the number of vertices in my graph. This is the case for all the algorithms that compute the tree decomposition. It can be always assumed, so we will assume it. From this decomposition, we can make this construction term, actually of size k square, sorry for this, that constructs this graph by just emulating this proof that I've shown you, forgetting vertices, then introducing vertices. Whenever I introduce a new vertex, I need to one by one introduce all the edges that are incident to it and so on, which means that all in all, I've got a k square n nodes of my term that constructs the graph. So I've got this many values, I've got this many values 2 to the k plus 1 times this times k squared times n values of this function phi that I would like to compute in a bottom-up way. And whenever I'm computing the next value, I can compute it in time polynomial in k. Well, actually, when you look at those formulas here, they usually involve just one or two other values. I would like to be a little bit careful about it because I do not want to speak about accessing memory cells in dynamic programming tables that are that have exponential size indexing sets. So I assume that just in the computation model, whenever I'm accessing a memory cell, it takes me polynomial in k time. So all in all, we've got this many values to compute. Each of them we compute in polynomial time. What we are interested in is actually the phi, the value of phi for the whole graph and say the empty set. This is assuming that at the top, at the root, the boundary is empty. That I can always forget all the vertices at the end. So this is okay, because this is just the maximum size of an independent set in the graph G. Yeah, by definition of my function H. So in this way, I computed all the values in a bottom-up way. Then I read the size of the independent set at the end. So I can conclude that I can find the largest, that I can find the cardinality of the largest independent set in a graph of Treewidth at most k in this running time, 2 to the k times polynomial in k times linear in the size of the graph, provided the graph is given with the composition. So this is just for argumentation that I can find the largest cardinality, not the set itself. However, it is quite easy to actually recover the solution from the dynamic programming. Whenever you're computing some value, you just record how you computed this value, what was the argument for which some maximum or minimum was obtained, and using this you can recover an optimum solution using standard techniques for dynamic programming. Good. So this is our first dynamic programming on a graph of bounded Treewidth, and it can be easily seen that this was kind of a generic approach in the sense that that we only need to understand what are partial subproblems, how to assemble partial subproblems, and what is the sort of behavior of a partial subproblem on the boundary. So this principle of dynamic programming on bounded Treewidth graphs can be applied to many more problems, and we will discuss it in a moment. But maybe if there are any questions at this point to this result. Okay, good. So let's look at the next example. I will be more brief here, especially when it comes to explaining the computation of the tables. But I would like to highlight a problem where the definition of states and the definition of this function phi is more complicated. So now let's look at the Hamiltonian cycle problem. So I would like to check whether a given graph has some Hamiltonian cycle. It's again an NP-hard problem. So let's think for now what is a partial solution in my graph. So a Hamiltonian cycle, when I have a graph and here is some boundary and there is some future to be constructed later on, yeah, and there is some Hamiltonian path that we expect to construct at the end of the day, then how it can interact with this part of the graph that we have already constructed? Well, it will not be just a Hamiltonian cycle of this graph, because this Hamiltonian cycle can go in and out and in and out and so on. So an intersection of a Hamiltonian cycle with this graph will be like a family of paths. For instance, I will go like here, yes, then maybe go back to the boundary, maybe use an edge in the boundary, go here and back. And then I will sort of think that I entered here and left here. Yes. Maybe I then again entered here, went a little bit, just touched the boundary, went back and went out. And maybe, for instance, this vertex was not visited at all because it will be visited like this in the future. Yeah. So this is how a partial solution can look like in my graph, and all the vertices here should be saturated by this system of paths. So a partial solution will be a system of paths with endpoints in the boundary that saturates, that visits all non-boundary vertices. Because I want that all the forgotten vertices are already visited by the Hamiltonian cycle. So now, when you look at such a partial solution, it has a kind of a behavior on this boundary that I will call a signature of my partial solution. So what I need to remember about such a partial solution in order to understand how I can extend it into the future. So first of all, for every vertex, I need to remember whether it is of degree 1, of degree 2, or of degree 0 in my system of paths. Yes. So how many edges incident to this vertex we have already encountered in my partial solution. Yeah, so for instance, this part, this degree mapping should look like this on the picture. So this is just a degree mapping that tells me from the boundary vertices how many edges I have already seen incident to it. Yeah, 0, 1, or 2. And second, I need to understand that, for instance, when I look at the degree 1 vertices, 1, 1, 1, 1, yeah, how they actually connect through paths. Because extending a solution that connects like this, like on the picture, yes, may be different than extending a solution that, for instance, joins this one to this one and this one to this one. Because at the end of the day, I would like to find one cycle and not many cycles. So I need to understand how the degree 1 vertices are being connected by this system of paths. So this I will encode in a matching on the vertex of degree 1. Yeah, so on the inverse image of 1 in this degree mapping, I need to define a matching. Yeah, to understand the connectivity that the system of paths is providing. So then the value that I will compute in my dynamic programming algorithm is for a given degree mapping and a matching. So this is the signature of my partial solution. I would like to understand whether there is a partial signature, there's a partial solution having this signature. So is there a system of paths in my graph H that saturates all the vertices that are forgotten, because I want all of them to be visited, and I would like to have this system of paths to have exactly this signature. Yeah. So note that now this value is a Boolean value. This belongs to true, false. In the previous dynamic programming, we're interested in optimization problem where we are trying to find a maximum size set that have some property. Now we are dealing with a decision problem, so my dynamic program will compute only Boolean values. Yeah. So how many states of the dynamic programming we have? So well, the boundary is of size at most k+1 always. So the number of signatures, well, for the degree mapping, we've got 3 to k+1 because there are 3 possible values for every vertex. And the number of matchings, well, I can bound by k+1 power k+1. And this is actually kind of tight. It's like k to k complexity. So for every subterm of my construction term, I will have that many to the order of k log k those signatures for which I will try to compute values. So in all, my dynamic programming will try to compute that many values, that many Boolean values, and again from the values in the root, I will be able to see whether there is a Hamiltonian cycle or not. Good. So now the tedious part of the dynamic programming is to actually give the recurrence formulas. So maybe I will not go like line by line through this. Let me just highlight some important facts about it. So whenever I'm introducing an isolated vertex, well, this vertex needs to have degree 0 so far because it has no incident edges. So if my signature is saying anything different than this degree should be 0, the value should be false. Yeah. Otherwise, this vertex doesn't matter. For I can just read whatever I computed before the introducing the vertex. When I'm introducing the edge, on the other hand, I can either ignore this edge when constructing a new partial solution. I can either ignore this edge and just read that before when this edge was still not there, I could make a set system, a path system that realizes my signature, or I can use this edge, and then I sort of need to make a big disjunction over all possible signatures d prime m prime that sort of can be extended to my signature dm that I'm interested in by adding this edge uv. And by extending, I mean that, for instance, if here is my edge uv, maybe here there was a path from some degree 1 vertex to u. These are boundary vertices. Maybe from V there was a path to some other boundary vertex of degree 1. And now this edge appears. So now I can glue those two paths into one path that goes from here to here. Yeah, so my d prime m prime would have in the matching this thing and this thing, while in dm I should have this as an element of the matching. And so this is written sort of informally. Well, you would need to understand what this thing means in terms of gluing a path on an edge to a signature. When we are forgetting things, when we are forgetting a vertex, we need to make sure that this vertex is saturated. So whenever we're forgetting a vertex, we can only forget a vertex that has already two incident edges. So whenever I'm looking at a signature on a trimmed boundary with the vertex forgotten, I need to look up the value whether there was a path system for which this vertex has already two incident edges. Yeah, so here this dv map to 2 means the extension of d by mapping v to 2. And finally, whenever we are joining two graphs, yes, again, it's a similar situation as with adding the edge. Whenever we have the boundary, yes, for instance, if my signature that I'm interested in says that from here to here I should have a path, then this path can be realized as, for instance, going first in my first element in H1. Yes. So in the signature in H1, I will have an element of a matching like that. Then maybe I will use some edge in the boundary, for instance, and then I will have an element of this matching in the second graph because I'm using a path in H2. So this signature dm that we are interested in can be sort of in many possible ways decomposed into a signature on the left and a signature on the right, yes, which together merge to a signature dm. And for this, you need to understand that there is a well-defined operator of merging the signatures. Yeah, so for instance, if I here have the boundary vertices, maybe the left signature looks like this, the right signature looks like this, and then they merge to a signature saying that in total, I've got a path from here to here, right? And then in order to see whether the signature dm can be realized in the graph after joining, I need to look through all possible dissolutions of dm into signature on the left and on the right, check whether the one on the left and the one on the right can be realized, and take a big disjunction over all possible combinations. Good. So this was quick. So I do not expect that you see all the details at once here, but I hope to highlight to you possible traps and possible issues that can arise when writing those dynamic programming formulas. During the tutorials, you will write a few more dynamic programming contrivs, so you will try for yourself how this works. Okay, so are there any questions? Should I repeat something that was unclear at this point? Can you put +1s in the chat if you're happy with that? Okay, good. I think the dynamic programming on bounded Treewidth graphs is also covered in the Algorithmica course, but we do it from scratch here as well, because there are subtleties that that need to be clarified, and also it's good to see it actually a few times in order to understand it well. Okay, so now this means that we've got that many values to compute in total. The overall answer will be read from the root back. And each value, each Boolean value we compute in running time now something like k power k, because observe that for instance, in the join node, yes, I was making a big disjunction over many different possible splits. And the number of possible splits, the best way is to actually go through all possible pairs and check which of them add up to my favorite signature dm. So this disjunction, I will still use exponential time like k power k in order to compute any single value dm. So now computation of one value actually doesn't take polynomial time, it takes exponential time. But all in all, doing all of this computation in a bottom-up way gives me an algorithm that solves Hamiltonian cycle on graph of Treewidth at most k in running time 2 to the k log k times n. Good. Let me just say that actually it is possible to make it better. The best possible algorithm now works in, I think, running time 4 power k times n. Times k to order of 1 times, let me write it like this. I don't want to say any false things here with respect to linear time. Good. So at the end of this lecture, I would like to touch one more topic, which is Courcelle's theorem. And this is a way of getting those dynamic programming algorithms bounded Treewidth graph sort of automatically from expressibility in a certain logical formalism. So as you've seen in both cases, the independence set problem and the Hamiltonian cycle problem, it kind of used the same principle. I define what is a partial solution. I define what is the interaction with the back and so on and so on. And I just do dynamic programming. And I give a recursive formula. So there is an automatic way of deriving such algorithm through expressibility in MSO2, which is the monadic second order logic on graphs with edge quantification. So before I give you a formal definition, let's look at some examples of formulas that express some properties of graphs and properties of different sets in graphs. So MSO2 is a language for defining properties in graphs. So for instance, I could say that this is an MSO formula ind of x, and this will say that x is an independent set in a given graph G. So how I could say that a set X is an independent set? I would just say that for every pair of vertices U and V, if they are both in the set X, then they should not be adjacent. Easy. Yeah, I just wrote it. Yeah. For instance, next I can write a formula saying that the graph G, that a given graph G is free colorable. How I would say this? I would say that there exist 3 subsets of vertices, A, B, and C, such that every vertex is exactly one of them. So I did not write this formula fully, but you can think how I would write U is in exactly one of them. I would write that either U is in A and not in B and not in C, or U is in B and not in A and not in C, and so on and so on. And then I will just say that A is independent, B is independent, and C is independent. Yeah, so this is quantifying that there is a partition of the graph into 3 independences, which is exactly free colorability. And finally, let's look at the example of writing a formula checking that the graph is is there a Hamiltonian cycle in the graph? So what's a Hamiltonian cycle? A Hamiltonian cycle is a subset of edges now, which is first of all spanning in the sense that it's connected and it reaches every vertex of the graph. And second, every vertex is incident to exactly two edges from my subset C. Yeah. So the degree with respect to the subset C of every vertex is equal to 2. Yeah. So how I would write this formula? Well, it's easy. There are just two edges that both are in C, that are different and are both incident to my vertex V. And second, whenever I take the third edge, G, that has these properties, then it must be either E or F. So this was easy. Spanning is a little bit more tricky. How do you say that something is connected? Well, for every subset of vertices, think of the subset, okay, maybe this is subset X and this is the complement of X. For every subset of vertices, either it is trivial in the sense that it is empty. So this means X is empty. Or it is cotrivial in the sense that X is the whole vertex set. And if it's neither trivial nor cotrivial, then there must be an edge that crosses the partition if I would like to say that C is connected. So this is exactly the definition of connectivity. However, I partition the vertex set into X and complement of X, I need to see an edge in the partition. Yeah, and this is exactly what I write here. There exists two vertices and an edge. These two vertices should be the endpoints of this edge. They should be on the other sides of the partition, and the edge itself must be from my subset of edges. So you see from those examples, what I can do in MSO2. So first of all, the variables of MSO2, I have variables for both vertices and edges, and sets of vertices and sets of edges. Yeah, so I can also use sets of edges here. And in the base case, I can write stuff like, for instance, U is equal to V. I can check membership. I can write that some vertex is incident to an edge, and I can write that two vertices are adjacent. Actually, I would even not need this one, because I could say, instead of saying that two vertices are adjacent, I could write there is an edge that is incident to both of them. And then given those atomic formulas, I can make larger formulas by doing Boolean operations, including negation, and I can do quantification, both existential and universal. And this quantification can be applied to all the variables of all the types. In particular, I can quantify over sets of vertices and sets of edges. Good. Are there questions at this point to the definition of MSO? Can I get +1s if the definition of MSO and how this logic works is clear? So it may be scary at first point, but this is just a language of saying of writing properties. There's no magic in here. No? So now I can write, if I have a MSO sentence. So a sentence is a formula without any free variables. I can write that a sentence is satisfied in a graph, and I will write it like that, and read it that phi is a model for G is a model for phi. And if I have, for instance, a formula with say one monadic variable, monadic meaning a set variable, and say a subset of vertices, I can write that in my graph the formula is satisfied on A. And this means I is satisfies my formula in G. So for instance, I could write independent that A is independent in G. So now Courcelle's theorem says that anything that you can express in this language, so like free colorability, Hamiltonicity, and so on, you can solve by dynamic programming on a bounded Treewidth graph. So there are many different versions. Let me highlight two most important ones: the decision version and the optimization version. So the decision version is very simple. I just get a sentence, and I've got a graph with a tree decomposition of width k, and I can decide whether my graph satisfies the sentence in time, that is linear time FPT parameterized by the size of the description of the problem and the width of the decomposition. So for instance, I wrote just a constant size formula saying that the graph is Hamiltonian. So from this theorem, I could get an f of k times an time algorithm for checking whether the graph is Hamiltonian. The f of k will be much worse than the one that we gave explicitly before, but it will still give you an FPT algorithm. And the optimization variant is kind of similar. The change here is that now I've got an MSO formula, say with one free variable, and now we can find a set that optimizes, say maximizes or minimizes cardinality, for which we can optimize the cardinality of this set, subject to a constraint that is given by an MSO formula. So for instance, using this formula for being independent, I could ask for a maximum size independence set in a graph, and this one I can find again in the same running time. Some function of the description of the problem and the width k times linear. So maybe this one I will skip, the proof sketch. The proof is actually really simple once we understand the right machinery. Maybe those of you who attend the course on finite model theory can already understand. Essentially, you are doing dynamic programming again, bottom up through the decomposition, and the state that the values that you are computing are types, MSO2 types of the boundaried graph that you are looking at of sufficiently large quantifier rank. And from RF games, you can get compositionality of these things, so you can compute the types for larger and larger boundaried graphs. Good, so let me now just highlight during the last, say, extended 3 minutes what will happen during the next lecture. Namely, we will be looking at the problem of computing the truth of a graph, because so far we have gave dynamic programming algorithm assuming that we are given a decomposition of the graph. So, but what happens if I'm just given the graph alone? Can I compute the decomposition quickly, and how quickly? So the problem is NP-hard in general, how to compute the optimum with the tree decomposition of a graph. However, observe that what we are actually interested in is that when we get the decomposition, we want to run some dynamic programming algorithm on it. And this dynamic programming will typically take time that is exponential in the value of the tree width. Yeah? So we can afford to have FPT a running time parameterized by the target value in the running time of the algorithm computing a decomposition. And then if you allow this, there are algorithms that do this. Here are 3 of them that I would consider the most important. The classical one is the algorithm of Bolander from the 90s, and this is an exact algorithm. It is given. All these algorithms are given the graph G and the parameter K, which is the target value of the tree width. So the Bolander algorithm either gives you a tree decomposition of width at most K, or it concludes that the tree width is larger. Yeah? So this is this kind of an algorithm. And the running time is quite a bit in K, so 2 to the K cube times linear in the size of the graph. If you want to have this factor better, the factor dependent on K better, then you can have it single exponential, 8 power K. But first of all, you need to have quadratic running time with respect to the size of the graph. And second, this is just an approximation. It will either tell you that the tree width is larger than K, or it will tell, okay, I did not manage to find a tree decomposition of width at most K, but here is a tree decomposition of width at most 4K plus 3. Yeah, so it's like a 4 approximation. Yeah, either tree width is too large, for your parameter, for the parameter that you gave me, or here is a tree decomposition that might be slightly too large, too broad with respect to what you wanted, but still it is pretty okay. So observe that in those 2 algorithms, there is a caveat that this one has a bad dependence on K, and this one has a bad dependence on N. you can actually, by having a 5 approximation, you can have both of the words. So you can have a single exponential dependence on k and linear time with respect to n. However, this algorithm from 2013, this is significantly more complicated than I think both of them. So what we will see at the beginning of the next lecture, is an algorithm, is the second algorithm, the 4 approximation algorithm of Robertson and Seymour. Will be slightly more relaxed with respect to the running time, and we will have a +1 in the approximation factor, but I hope that it will be okay. If you want to have the tight, if you want to see the tight analysis of this algorithm, the Platypus book contains a streamlined explanation of this as well. Good. So this was the trailer of the next lecture. Are there any questions at this point? Okay, right. So if not, then I am now finishing the recording. So thank you very much